Okay, year 13. So, I've talked about colour a lot, and I've shown you just in the last video the copper hexa-aqua 2 ion and the tetrachlorate copper 2 ion having different colours. And that's partly because they have different geometry, but also because they have different ligands attached to them. What you need to be able to explain is, why do transition metals have colour? Why are these solutions coloured? Well, it's to do with the shape of the d orbitals, and we need to look at the shapes of the d orbitals, which looks quite complicated to start with. My diagrams are, as usual, brilliant, and these three are supposed to be completely identical. They're not, are they? But they're supposed to be. I will send you a nice document which will show it much better. First of all, notice how lobular the d orbitals are. They're even more lobular than the p orbitals. They have a greater radial distribution function, if you want to sound fash, or you could just say they're more lobular. There are three, because there are three axes in 3D that look exactly the same. They're the dxy, where we have x and y on two of the axes. There's the dxz, where we have x and z, okay? And there's the dyz, which we have y and z on any of those two axes. Notice how that these lobes point 45 degrees, not at the axes, directly in between the axes, if you like. They're not pointing along the axes at all. The other two are called the dx squared minus y squared. This one points directly along the x and the y. It looks a bit like one of these. It's actually slightly stubbier in terms of the way these lobes are. The key thing that you need to know is this points directly along the x and the y. And there's one that's very odd, the dz squared, which it has one very big lobe that points just along the z axis, and then has a weird donut shape here. Now, I've probably explained to you before that a subshell can actually be a complete sphere. And if we added all of these together, we'd find we'd need this little horseshoe to complete the middle bit, because these are so lobular, they go out so far. We actually need this little area here to make it into a complete shell. The full 3D is very shielding, as you can imagine. 3D10, it's very, very shielding indeed. Anyway, let's move on now and talk about why these have colours. Well, if we don't have any ligands around it, all the d orbitals are the same energy level. They're said to be degenerate. So if this is energy going up here, at the moment here we've got 5 d orbitals. The 5 that I've shown you, they're all the same energy. Okay, that's not very well drawn. Let's make them really, really close together, so they're all like this. All 5 of them are the same energy. Now, if we look again at our hexa-aqua ion here, you'll notice that if you are an orbital that like the dx squared minus y squared, let's sort of superimpose that on here. And imagine this is the x-axis, and this is the y-axis. So any electron stuck in the dx squared minus y squared is, unfortunately, it's got 2 electrons being shoved right into it. It's not going to be very preferable to be an electron where you are pointing directly at along one of these axes where the ligands are coming from. So not surprisingly, the dx squared minus y squared is much higher in energy than it would normally be. Now we've got the ligands around it. And the other orbital that's a bit unfortunate is this one, the dz squared. So the dz squared, going back to my diagram here, you can imagine there's the z-axis, and the dz squared is also pointing directly at a ligand. So remember, orbitals are areas of space where electrons can occupy. So it's, bear in mind that ligands are shoving electrons into these partially filled orbitals, means that these two are going to be much higher in energy. If you want to be an electron in an orbital, you want to be in these three, because you're pointing therefore in between. So if we sort of superimpose one of these, look, it's right in between where the ligands are pushing. So these three are now lower in energy. The dxy, the dyz, and the dxz. These are now much lower in energy as a result, because they don't have ligands shoving dirty, great big lone pairs of electrons into them. We now have 2 energy levels. We have these 3 orbitals down here, and these 2 orbitals out down here. Now, if we have anything from D1 to D9, we have the ability, imagine D1, this, if an electron will be in here, it can, if given enough energy, be promoted to the other two. That energy with transition metals is always in the visible wavelengths of light. So the energy is given by HF for you physicists, and the frequency here, this is Planck's constant, the frequency here, this delta E here, always happens to be in the visible wavelengths of light. So going back to copper, we know that this appears to be blue. Why? Well, this is a D9 system, so it actually has it mainly filled. It's just got one vacancy up here, and one electron can get promoted up to here. It will absorb in the red range. So the reason why this looks blue is because all the red light is being removed. That's why things in nature are coloured. They're not emitting any colour, not like a laser or a torch, or a flame test. It's actual absorption of energy that's going on here. And the colour you see is the complementary colour, the colour that's left. So copper appears to be blue. Why? Because most of the red light has taken out, and therefore all you've got left to see is the blue.